3I-ATLAS is now making its closest pass to Earth, and we've been following it every step of the way. For months, we tracked the strange jets that stayed locked in place, the industrial nickel in its makeup, and the hidden burn behind the sun. Now there's a new development. As the object moves closer, telescopes are picking up a green glow around it, and scientists are seeing new shapes forming in the gas cloud. But can a normal comet really turn green and grow new features this close to Earth? And what happens if the most important changes are happening right now while everyone's watching? A color change no one expected. If you've been following the latest images of 3I-ATLAS, the most obvious change is also the strangest one, because the comet isn't just getting brighter as it approaches Earth, it's taking on a clearly green glow that wasn't there before, and that combination is what has scientists watching it very closely right now. So what exactly are we seeing in these new images? In simple terms, the comet's coma, which is the fuzzy cloud of material around its solid core, is brighter overall and more green than it was earlier in its journey, and that shift isn't small when you compare recent observations to images from just a few months ago. This isn't a trick of your screen or a single heavily edited photo either, because several instruments and color filters are picking up the same trend, which tells scientists that something real is changing in the comet's behavior as it moves closer to us. Does a green comet automatically mean something strange or unusual is happening? Not really. Green comets are actually a known and studied thing, and the most common reason for that color is a molecule called diatomic carbon, usually written as C2, which forms when carbon-based materials break apart under sunlight and then glow as they interact with the sun's energy. When comets heat up, these molecules can escape into the coma, and when sunlight hits them, they give off a greenish light that telescopes are very good at spotting. In that sense, green is often a sign of an active comet, not a mysterious one, and many well-known comets in our own solar system have shown similar colors when they moved closer to the sun. But here's where 3I-ATLAS becomes interesting again, because while the green glow itself isn't unusual, the timing and the change from earlier observations are what make scientists pause. Earlier images of 3I-ATLAS didn't show this strong green signal at all, and in fact, some observations suggested the comet looked redder, which points to a different mix of materials making up the coma at that time. That tells us the comet's output isn't staying the same, because as it heats up, it's releasing different material, and that strongly suggests that sunlight is now reaching new layers beneath the surface. Think of it like a frozen object with several layers, where the outer layer reacts first, and deeper layers only start to respond after enough heat slowly moves inward. When those deeper layers finally warm up, they can release new gases that weren't escaping before, and that's one of the simplest ways to explain why the comet's color is changing instead of staying constant. Another important point that often gets lost in headlines is the difference between a comet getting brighter and a comet getting greener, because those two things don't always come from the same cause. Brightness is often driven by dust, meaning tiny solid particles that reflect sunlight very well, while color, especially a green color, is usually driven by gas being released. So when you see reports saying the comet is brighter and greener, it's easy to mix those changes together as one event, but scientifically, they can be caused by different processes happening at the same time. A comet can brighten because it's throwing off more dust, while the green glow increases because a specific gas like C2 is becoming more common in the coma, and separating those signals helps researchers understand what's actually happening at the source rather than just what looks dramatic in pictures. This brings up another question that's easy to ask but harder to answer. Why can't we just look at a picture and know what's going on? The answer is that still images, even very sharp ones, hide a lot of important information. A single frame freezes a moment in time, which means it can't show rotation, short bursts of activity, or repeating patterns that only become clear when you look at many images taken over hours or days. If the comet is spinning, for example, one side might release gas more strongly than the other, and that can make the coma look different depending on when the image was taken. A brief burst of activity could also brighten the coma for a short time, then fade again, and if you only catch one of those moments, you might think the comet has permanently changed when it hasn't. There's also the issue of viewing angle, because the way a jet or stream looks depends on how it's angled compared to Earth and the Sun, so a narrow stream of gas can look faint or even invisible in one image and suddenly stand out in another just because the viewing position changed. This is why scientists depend heavily on time-based observations, where they track how the comet behaves across many images instead of relying on a single snapshot. When you only see one image, you're missing movement, repetition, and background, which are often the most important clues for understanding comet activity. Now think about what's at stake as 3I-ATLAS continues its approach toward Earth, because this is where even small changes start to matter much more. As the comet gets closer, sunlight becomes stronger, and any internal heat that's been slowly building up has a better chance of triggering new activity, including the opening of fresh vents or changes in existing jets. These vents act like release points, letting gas and dust escape more forcefully, and even a small shift in chemistry could be a warning sign that something new is about to happen. This doesn't mean a dramatic explosion is certain, but it does mean scientists are watching closely for signs that the comet's behavior may be about to change again. Next up, we're going to explore the unsettling possibility that what we're seeing right now isn't the peak of activity at all, but a quiet phase before the comet reveals something far more telling. What happens beneath the surface? One of the most important things to understand about comets, and something that often gets overlooked, is that heating does not work like flipping a switch, because sunlight doesn't instantly warm a comet all the way through the moment it gets close to the sun. So why do scientists keep talking about delayed reactions when it comes to comet activity? The answer is simple but powerful. Heat moves slowly through solid material, especially material that's cold, porous, and layered like a comet's nucleus. When a comet swings past the sun, the surface heats up first, but the interior can stay cold for weeks or even months, which means activity can actually increase after the closest approach rather than during it. This is why scientists are not surprised when a comet suddenly becomes more active later on, because in many cases, that's when heat finally reaches deeper layers that haven't reacted yet. As that heat moves inward, the chemistry starts to change in a very real way, because comets are not made of one uniform substance, but of layers that formed at different times and under different conditions. The outer layers might release simple gases first, while deeper layers can contain materials that only escape once enough heat builds up below the surface. When those deeper layers finally warm, they can release new molecules into space, and that can directly change the color and brightness of the coma. This is one of the strongest reasons scientists think the color changes in 3I-ATLAS matter, because they suggest we're not just seeing more activity, but different activity, driven by materials that were sealed inside until recently. In simple terms, the comet isn't just doing more of the same thing, it's doing something new because new material is being exposed. Here's a question that sounds obvious but matters a lot. If the chemistry is changing, why doesn't the comet always look the same from night to night? The reason is that jets play a huge role in how comets look, and jets are not evenly spread across the surface. A jet is a focused stream of gas and dust escaping from a specific area, almost like a natural exhaust vent, and depending on where that vent is located, it can make the coma look lopsided, brighter on one side, or even oddly shaped. If a jet is narrow and strong, it can dominate the entire appearance of the comet, and small changes in its strength or direction can completely change what telescopes see. This means that even if the total amount of material being released stays the same, the comet can still look very different just because of how and where that material is escaping. Viewing angle makes this even more complicated, because the way a jet appears depends on how it's pointed relative to Earth and the Sun. A jet that's aimed slightly toward us can look bright and sharp, while the same jet viewed from the side might look faint or spread out. This is why scientists are careful not to draw big conclusions from a single image, because geometry alone can explain a lot of visual changes without requiring anything dramatic to be happening physically. When you add rotation into the mix, things get even more interesting, because a rotating comet doesn't vent material evenly over time, it pulses. As the nucleus spins, a jet might face the sun for part of the rotation, heat up, release gas, and then shut down again as it rotates back into shadow. This can create repeating patterns where the comet brightens, fades, and then brightens again in a way that looks unpredictable unless you're tracking it carefully. So could rotation really explain sudden changes in brightness or color? Yes, and scientists have seen this many times before, because rotation can act like a natural timer that controls when different areas of the surface become active. If one region contains a certain type of ice, it might release a specific gas when heated, producing one color, while another region releases something different later on. When these regions rotate in and out of sunlight, the comet's appearance can shift in ways that seem sudden but are actually very organized. This is why astronomers look for repeatability, because if changes happen on a regular cycle, that's a strong clue that rotation is playing a major role rather than a random outburst. At this point, it helps to step back and compare 3I-ATLAS with the only other interstellar visitors we've ever studied. The first, 1I Oumuamua, didn't behave like a classic comet at all, showing strange motion without a visible coma, which forced scientists to rethink how outgassing can work when it's driven by unusual materials. The second, 2I Borisov, looked much more like a traditional comet, complete with gas and dust, which initially made scientists feel more comfortable applying standard comet models. So where does 3I-ATLAS fit in? Right now, it seems to sit somewhere in between, because while it clearly shows comet-like activity, the timing, chemistry, and structure of that activity are raising new questions that don't have simple answers yet. Please subscribe channel.